All right, good morning. Y'all ready to get going? Any questions over the first set of problems from 6.6? The type 1 improper integrals? We're all okay? All right, we're gonna finish up 6.6. We're gonna start chapter 7 today. So I told you last time we have two types of improper integrals. The first type involved infinite intervals. So type 1 was infinite intervals. I'm going to be saying intervals and integrals today, and they sound the same. So be a little, if you have a question, just let me know. Like, did you say integrals or intervals? So we have infinite intervals. It was type 1. And the thing that's nice about the type 1 is that you can kind of always tell when you have one, because you're going to either have an infinity up here, or you're going to have a negative infinity here, or we're going to have infinity, infinities on both ends. And then you're a type 1. Type 2 is different, all right? Type 2, you don't necessarily know that you have it unless you're looking for it, which means we always have to be mindful that we might. So type 2, we have infinite integrands. And I think the easiest way to get started with this would be to look at first a problem we did last time, which was the integral from 1 to infinity of 1 over x dx. We did that last time. You can look in your notes. We determined that diverged. Right? So that meant that the area underneath that graph from 1 to infinity was infinite. Okay, so this area here, it diverged, but it was actually went to positive infinity. Okay, well, let's look at this new integral for today, the integral from 0 to 1 of that same function. So now instead of looking from one out to the right forever, we want to be looking at 0 to 1. So we know at 1 we get 1. But what do we get at 0? When we plug 0 into this function, what do we get? It's undefined, right? It's undefined. So if you graph this function, we actually have a vertical asymptote over here. So the y-axis goes up, and our graph, just as we approach y, this thing takes off to infinity. So now we want to know, what's the area under here, including all of that stuff all the way up forever. So again, we have a region that looks like it's infinite, right? Because of the asymptote, we have the infinity idea, just like we did when we went out to the right forever. But do you see that it's not obvious from this? It's not obvious that you have a problem. You would have to recognize that 0 is not in the domain of this function. So you have to recognize that, and that's what makes it a type 2. If I had changed this problem to this, integral from, let's say, 1/2 to 1 of 1 over x dx, then this is not an improper integral, because if you look from 1/2 to 1, this is a defined function. There's no problems. So that would just be your traditional definite integral. You just go and do, find the antiderivative, plug in the two endpoints, subtract, be done. But this type 2 is unique. So what we're going to do is very much like what we did with the last problem, with the type 1s. Hold on, I've got some. Remember what we did with the last one is that if we wanted to go from, let's say, 1 to infinity, we went from 1 to b, we stopped at b, or sorry, not b, we used t. We stopped at t, and then we took the limit as t went to infinity of the integral from 1 to t, right? That's what we did. So how do you think we could do this a similar way using a limit? What could we do? Any ideas?
What's the limit as it approaches 0?
Okay, so let's do that. How about we do the limit as t approaches 0 of what integral? From where to where? So where do we have the problem, at 0 or at 1?
At 0.
0. So we'll replace that with t and leave that as 1. So essentially, here's what we're doing. I'm going to erase, oh, I'll leave that one up there. What we're doing is this. We're saying, all right, we're going to find the area between some value t and 1. We're going to try and come up with a formula for that area. And then what we're going to do is we're going to let this t slide to the left and approach 0. Make sense? Instead of taking it out to infinity like we did last class, we're going to just let that t get real close to the 0. Now we have to be really careful with something here, because when we approach 0, if you go back to Cal 1, if I say, hey, you know, let x approach 0 or let t approach 0, you have to be clear which side you're coming in from. If I don't tell you which side to approach from, then you have to approach from both sides. Here, we're only interested in approaching from which side? Which side of 0 are we approaching from, the left or the right?
From the right.
From the right side. So in this limit, we need to put a little plus on the top right-hand corner of that 0. See, I put a plus. So this is what we call a single-sided limit. We are only coming in and taking the limit from one side. And then we'll work through the rest. Is this basic idea make sense though? Yes? Okay, so what I want to do is I want to start the whole thing over, because I want you to kind of see how I go about something like this. Okay, so what I do is I look at this and I say, okay, I have a problem at 0, right? I have a problem at 0. So I like to draw the interval. I like to actually draw the interval that we're integrating over, 0 to 1. And then what I do is I recognize that 0 is a problem. So I come over here and I circle 0. And I say, okay, that's where I have a discontinuity. That's where my function is not continuous, that 0 is not in the domain. So what I'm going to need to do is I'm going to need to approach 0 from the right-hand side. Now I'm not coming from the left because my interval doesn't even involve the left-hand side of 0. It only involves the right-hand side of 0. So that means that I'm going to set up a limit. I'm going to let t approach 0 from the right of the integral. I'm replacing the 0 with t, leaving the 1 a 1, and then I have my function. And then we just do what we did last time. Let's just leave the limit here. We're going to do the limit at the very end. We're going to find the antiderivative of 1 over x, which is the natural log of the absolute value of x, from t to 1. And I did not put absolute value of x. And the reason I didn't do absolute value of x, can someone tell me why I didn't bother with the absolute value?
It's not going to be negative.
That's right. Our interval is from 0 to 1. So those are always positive numbers. So I don't need to even worry about x being, or anything ever being plugged in as being a negative number. So I can just get rid of the absolute value. Generally speaking, though, you can't. It's only because of the interval we're looking at. Okay, so now we come through and we say, all right, limit, t goes to 0. We're approaching from the right. We're going to plug in two things. We're going to subtract, and we're going to take a limit. So plug 1 in first, so natural log 1, and then plug in t, natural log t. And the one on the left, we can calculate. Natural log of 1 is just 0. But now we have to do this limit. We need to take the limit as t approaches 0 from the right of natural log of t. Can somebody tell me what that limit is and why it's that limit? What could you use to help you understand what's happening there? You can't plug 0 in, right? Does everyone agree with that? If you go try and type in natural log of 0 on your calculator, you're going to get an error.
I think it's
Table?
0 because it's slowly approaching 0 as it keeps going up.
What's approaching 0?
T.
So t is approaching 0, right? So you're letting this number get smaller and smaller and smaller, and you're plugging it into the natural log. So what does the natural log function do as it gets closer and closer to 0? So this is where you knowing what the natural log function looks like would help. So if you go back to algebra, your natural log function looked like this. That's what natural log of x looks like. So as you approach 0 from the right, as you get closer and closer to 0, where are you headed?
Negative infinity.
Negative infinity, right? It's asymptotic. So what we know is that this, in the limit, right? When you take the limit, this thing is going to minus, and then that's going to infinity. So what can we say about this improper integral? Are we getting a numerical answer? No, we're getting infinity. So the limit doesn't exist, which means that it diverges. So everything is the same as type 1 in terms of what your answer is. If you get a number, then it converges to that number. If you get something other than a number like infinity or negative infinity, or if the limit doesn't exist, then you'd say it diverges. Okay? Oh, you know what? I messed up. Sorry. This is going here. That's going to negative infinity. Sorry, this thing is diving to negative infinity, right? And then we have a minus there. So minus would be plus. So the area is getting bigger and bigger and bigger. It's becoming positive infinity. So that means on this graph that we were looking at, we were trying to figure out right here what this area was. And what we just determined is that that area is infinite. And that's also what happened when we went from 1 to infinity, right? When we went to the right this way, it was also infinite. Okay, let's do another one. Let's go 0 to 1 again. This time, let's do 1 over x cubed. Any guesses as to what's going to happen? Any guesses? Do y'all remember what happened to that last class? When we went from 1 to infinity, do y'all remember what happened? Here's
Didn't
last
it
class.
get there quicker?
Yeah, it got there quicker, and we actually came up with the final conclusion. Remember that from class last time? We said if you're integrating from 1 to infinity and you do 1 over x to a power, then if that power is greater than 1, you're going to have convergence. But if the power is less than or equal to 1, you're going to have divergence. Now that's from 1 to infinity, so that's a type 1. We're not talking about that, but I'm asking you what you think. You know, to the right, if we go from 1 to infinity on this one, it's going to converge. What do you think is going to happen if we go to the left of 1 towards 0? Do you think it's going to converge or diverge?
It's going to diverge.
Think it's going to diverge? Think it's going to do the opposite? Okay, let's see. Well, we have to realize we have a problem, right? We have to realize that the endpoint there, 1, is a problem. So we're going to approach it from the right. So we're going to set up a limit. T is going to approach 0 from the right. And we are going to replace the lower limit of integration with T. Then we have to go find the antiderivative. And what is the antiderivative of this? So rewrite that as x to the negative 3. I think that'll be easier if you just do that and do your power rule. So what is that? Negative 1/2 x to the negative 2 evaluated from t to 1. And I'm going to rewrite that limit t approaches 0 from the right. Let me just rewrite it first. I want to look at it like this. I want to bring that x and -2 down. I think it'll just be a little bit easier for us to analyze this. Any questions? Okay, now I'm going to plug in my two endpoints. So I don't have to do a limit. So when I plug in 1, I get -1/2. And when I plug in t, I get -1/2t squared. This first part's just -1/2, nothing happening there, then minus. And now let's figure out what's happening to this piece. We're taking the limit as t approaches 0 of -1/2t squared. So does someone know where that's going? The numerator is -1. What's your denominator approaching? I'm going to eat something, so I'm going to turn my camera off. No? Don't know where that limit's going? Limit, t approaches 0 from the right, of -1/2t squared. The numerator's just stuck, right? It's fixed. And it's negative also, right? It's a fixed negative number. And where's the bottom headed?
Infinity?
No, t is approaching 0. Are you giving me the final answer, or are you giving me what the, I'm just asking right now what the bottom is headed towards.
Yeah, so I was thinking if you plug in numbers closer to 0, like 0.0001, that number is actually getting bigger.
The whole thing is getting bigger, right?
Yeah.
So as the denominator gets smaller, the fraction gets bigger. So look, everyone, this is a Cal 1 concept. If you take a limit, all right, doesn't matter what it is, okay? If you ever get a fixed number over something that's approaching 0, your answer is either infinity, -infinity, or does not exist. Those are the only 3 outcomes that can happen. You have to determine which of those 3 it is. And so what you do is you try and figure out the signs of the numerator and denominator. Figure out, is the top a positive number or is it a negative number? And on the bottom, is it positive or is it negative? And then you just use whatever those ratios are. If you have a negative on top and bottom, then your answer is positive. If the signs are different, then you get a negative infinity. So for us here, we had a fixed number on top, right? -1, that's a negative number always. And then on the bottom, we're approaching 0. I put a little plus sign here because think about what 2t squared would be. Yes, it's getting smaller, but it's always positive, right? It's always positive because, well, there's a couple of reasons it's positive. You're plugging in a number that's to the right of 0. So you're plugging in a positive number and then you're squaring it. So it's definitely positive. Multiplying it by 2, it's positive. So what would happen here is you have a negative number over a positive number. So your ratio must be negative, and therefore you can conclude it's -infinity. So what does this integral do? Looks like it diverges, right? -1/2 plus infinity. Divergence. Yusuf was correct. All right. What about this then? Now compare that to this. If we would have done that this last class, would that have converged or diverged from last class, this one?
Converged.
Converged? What's the power?
Diverged.
Now would have diverged, right?
Yeah, this is the same as 1 over x to the 1/3, right? And therefore the power is less than 1. And that would have meant that this diverged. That's from last class. What's going to happen here? Is it also going to diverge, or is it going to be the opposite? Like Yusuf said, right? Because we just said the same thing for this one. This one, if we look from 1 to infinity, converged, but if we went from 0 to 1, it diverged. Here, this one from 1 to infinity diverges. Maybe this converges. Let's see. So we have a problem, right? We have a problem at 0. So I'm going to approach that from the right. So this becomes a limit. T approaches 0 from the right. Integral t to 1. I'm going to go ahead and rewrite that as x to the negative 1/3. I'm going to get myself ready for power rule by bringing that thing up. This should be limit t approaches 0 from the right. Okay, the antiderivative of x to negative 1/3. You have to add 1 to that. If you add 1 to that, you get 2/3, and 1 over 2/3 is 3/2. So you have 3/2 x to the 2/3 evaluated from t to 1. Yeah, okay. And now limit t approaches 0 from the right. Going to plug in two things here. Plug in 1. Well, what's 1 raised to any power?
1.
1. So this should just be 3/2. And then plug in t, 3/2 t to the 2/3. And what about that limit? When we do this limit, if t approaches 0, and we just plug 0 in here,
It's 0.
It's just 0, right? Because that's t to the positive number, t to the 2/3, which means the cube root squared. So you're taking 0, you're taking the cube root, you're squaring it. That's going to be 0, getting closer and closer to 0. So this time we get 3/2 minus 0, which is 3/2, which means we have convergence. So we're not going to go prove this, okay? But we do have a conclusion we can draw from this. The integral from 0 to 1 of 1 over x to the p dx can be two different things. It will converge if the p is less than 1, and it will diverge if the p is greater than or equal to 1. So we're not proving that, I'm just telling you that that's the case. We've shown it work. We've shown this in the 3 examples we've done. They fit into this format, but just doing 3 problems doesn't prove anything. You'd have to go and like generally prove this like we did last class, but I'm not going to take time for that. You're just going to take it on faith, right? All right, let's do another problem. Now, I want you to watch me do this problem incorrectly. I hate to show people the wrong way to do something, but let me just show you the wrong way. Okay, so I look at that and say, oh, wait, I know how to find the antiderivative of that. Okay, that's a constant over linear. We did this for last test. So I know the antiderivative of that is natural log of the absolute value of x minus 3. I'm going to evaluate that 0 to 6. That's going to be 2 things subtracted. It's going to be plug in 6 first, and then plug in 0. And that gives me the natural log of 3 minus the natural log of, let's see, I do 0 minus 6 is negative 6. Take the absolute value, get natural log 6.
Wouldn't it be
And
negative 3?
Pardon?
You put you put -6 and not -3, like the natural
Oh,
log
yeah,
of x minus
yeah,
3.
sorry. Thank you. That's 3. Yeah, I don't know why I did that. That's weird. Okay, so natural log 3. Thank you, Peggy. And I don't need the absolute value because I already took the absolute value. So what do we get here? 0.
0.
So it converges. That's wrong. Everything's wrong. Why?
You didn't put your limit.
Yeah, well, why do I have to do a limit, Ross?
That's just what we're doing.
Yeah.
I don't know exactly why.
Where are you
why.
integrating from? The interval goes from where to where?
0 to 6.
0 to 6. Do we have any problems between 0 and 6 with that function?
Maybe the number
Yeah.
3.
At the number 3. At the number 3, we have a problem. See,
So there would be a
doesn't have
hole?
to be an endpoint, okay? It doesn't have to be an endpoint. It can be any point in the interval. So we have an issue here, all right? So what we have to see, this is what makes type 2s dangerous, is that sometimes you don't see that there's an issue when there is, and then you go do what I just did, and then it's all wrong. So what we have to do here is draw our number line, 0 to 6, identify where we have a problem at 3, and I hope everyone's clear that at 3, this thing is undefined, right? You can't plug 3 in here, you get division by 0, which is not okay. So what we're gonna do now, shit, what are we gonna do now? What do you think we're gonna do now?
Split it into 2.
Do 2, okay? Because we've got to approach 3 from both sides. So we're gonna split the integral up into two integrals. Right, so we're going to do this. We're going to go, all right, let's do the integral from 0 to 3 first. Figure out what that is. Whatever that answer is, then we'll do the integral from 3 to 6. Now, splitting up an integral into 2 pieces like that by subdividing out or partitioning out the number line, the segment, is something we've done before, so that's not new. What's I guess different now is that we're going to have 2 separate limits we have to do. So on this first one, okay, on this first integral here in orange, I'm going to be approaching 3 from which side? So the orange part is from 0 to 3 like this. So which side of 3 are we approaching from, left or right?
Left.
The left.
So this is going to become the limit as t approaches 3 from the left of the integral. Which am I replacing, the 0 or the 3?
The 3.
The 3, right? Because that's where the problem is. So 0 to t of 1 over x minus 3 dx plus, now we need a new limit, right? This is a different limit for a different integral. I'm going to use r approaches 3 this time from the right side, because we're in the interval 3 to 6, so we're going to come in from the right as opposed to the first one we came in from the left. So we're going to approach from the right. We're going to replace the 3 with r, that's the bottom limit of integration, leave the 6 alone, like that. Any questions? All right. We need the antiderivative of each of these. So the antiderivative of the first one, we already did that, natural log of, I don't need the absolute value, or do I?
Yes.
Is it possible to plug in a value of x that would give you a negative?
Not in this interval.
Well, the interval won't. The interval won't, but is there an x that when you plug it in, you would get a negative?
Oh, yes.
Right? Like, just imagine if you plug one into the answer, right? Like if I just left this as x minus 3, then if I plugged in 1, I would get a negative in there, right? So we do need the absolute value this time. So a good rule of thumb is just to always leave it there, all right? If you don't want to ever get in trouble with it, just leave it all the time. Okay, and then we're going to go from 0 to t here. Then we have to do plus the limit as r approaches 3 from the right. The antiderivative is natural log absolute value of x minus 3, evaluated from r to 6. Limit t approaches 3 from the right, and then I'm going to have two things subtracted here. And then I'll have another limit as r approaches 3 from the right, and I'll have two things I'm going to subtract there. All right, t goes in first. So natural log absolute value of t minus 3, and then natural log of 0 minus 3, absolute value. And then the other one, I'm going to do natural log of, I'm plugging the 6 minus 3, absolute value of that. The natural log of absolute value of r minus 3. There we go. I'll look at the things that I have no issues with first. I have the minus sign here, and that's just natural log 3. That's what that is. And then over here, this is also natural log of 3. So I have a plus, and then I have natural log 3, and then I have minus. And so I've got to figure out this yellow part, and I've got to figure out this blue part. So let's do the yellow one first. Are there any questions? What happens as t approaches 3 right here? What is the inside of this heading towards?
0.
0, and it's absolute value, which means it's positive, right? So it's headed to 0 through positive numbers and then getting plugged in a natural log. So what does the natural log do as you plug in things that are headed towards 0 from positive values? Well, didn't we just do that a little while ago? That was the graph of the natural log diving down to what? Negative infinity. So this heads to negative infinity. And at this point, we can stop, because you have, this goes from last class also, is that if you ever have an integral and you split it into 2, the only way that the whole thing can converge is if everything converges. So if one of these two integrals diverge, the whole thing diverges. So because of this right here, because of this result right here, that's going to negative infinity, we can say that the whole thing diverges. And remember, when I did the problem earlier, I said the answer was 0, that it converged. That's incorrect. So if you look at this graph, 1 over x minus 3, and we look at it on the interval 0 to 6, you can see the asymptote in here. And so what we're doing is we're trying to find the area, right? And we have this vertical asymptote here at 3. Now, somebody is going to tell me right now that the answer should be 0. But, I mean, do y'all see why the argument that this answer should be 0 would kind of make sense? Look at, isn't this symmetric? Isn't this area here like symmetrically the same as this area here? Just one of them is above and the other one's below, right? So it seems like your answer should be 0. But our answer is actually that it doesn't converge, it diverges. And this is one of those weird places in math where it's the definition of what it means for an integral to converge. It's the definition that's making us draw our result. The definition of convergence means that when you do the limit, you get a number. All right? That's convergence. Divergence is everything else. And this answer that we got falls into the category of everything else. So our answer has to be diverge, just by the definition of what it means to diverge. All right? We're not saying that the area is infinite. We're not saying that the area is negative infinite. We're just saying that it does not converge. It's kind of weird, huh? All right, I have another one for you. I'm going to let you play with this one for a few minutes. See what you think. All right, why don't I give you, I don't know, let's take a few minutes. Let you try and see if you can't get this thing set up and maybe even start trying to find the answer. I'm going to start working it out without saying anything so you can look up and see if you're getting the same thing. So no one has questions. Everyone's good. What do we do now?
Try to find out the integral of x minus 3 over x minus 2.
So how are you going to do that? All right, that's what we need to do now. This integral is not as straightforward as the ones we've had up to this point. So with a drum roll in the background, let's see, who's got the answer? How you integrate that?
I did long division.
Good, excellent. X minus 3, so this is partial fractions. Long division.
It'll be 1
Yep, keep going.
plus 1 over x minus 2.
You get a negative, or because you have to change the
Oh,
sign.
yeah, negative, sorry. Minus 1 over x. Yeah.
So plus negative 1 over x minus 2. Good. Okay, and that you do not need to do any more work, right? You can do the antiderivative of each of those. The antiderivative of 1 is x. I'll bring that minus there, and that's a constant over linear, so natural log of x minus 2 plus c. So that's our antiderivative over here. I gave a problem like this to my class yesterday, and no one could come up with long division. Everyone was trying to do crazy shit. They were like trying integration by parts and just so good. So look, everything we've done is now on the table. Okay, when we finished up, remember when we finished up partial fractions, we started talking about problems from chapter 5. And I told you that, hey, the problems in chapter 5 won't be that hard because you haven't learned the integration. But now we're in chapter 6, section 6. So we've covered all the integration techniques. So when you see these problems, you might have to do, integration by parts, basic U sub, trig sub, partial fraction decomposition. It's all there now. Okay, so now continuing. And I hope this one converges. I don't think it's going to though. What the hell am I doing? Oh, antiderivative. Evaluated 1 to t plus, now I have another one I have to do over here. I'm kind of skeptical, so I almost want to do the first one and then deal with this one in a minute, because if the first one diverges, I'm going to be done. Okay, plugging in my 2 endpoints. Plug in t. So t minus natural log t minus 2. And plug in 1, I get 1 minus natural log of 1 minus 2. And do you all see that on the first one, this goes to 2 minus the natural log absolute value of 0? Like in the limit on this first one, when I replace the t with 2 here. And because it's an absolute value, it's always going to be approaching 0 from positive numbers. So this is the third time we've seen this now. That heads to negative infinity. So we can say it diverges. Didn't even have to do this one. Didn't even have to do it because the first one diverged. Do we have any questions? No? Do I need to leave that up there, or can I move on? Move on? Okay, how about this one? Is this improper? You have a problem anywhere? At 0, right? All right, so number line. We're going from 0 to E. Remember, E is just a number, right? About 2.718. Our problem is at 0, though. So we're going to have to approach it from the right. Limit T approaches 0 from the right of integral T to E, natural log x over square root of x dx. Who has the antiderivative, or at least how to go about it?
Integration by parts.
Good, okay. If I'm doing integration by parts, what are you going to choose for the u?
Natural log of x.
Natural log of x. Then the derivative of that's just 1 over x dx. That forces you to use what is the dv though? Be real careful. What's dv?
X to the negative 1/2.
X to the negative 1/2. So it can't, it's not, be careful, it's not square root of x, right? It's 1 over the square root of x. So we can rewrite that as x to the negative 1/2. And then when we do the antiderivative of that, we get 2x to the positive 1/2. So then this turns into ultraviolet minus voodoo. Okay, when I do the voodoo part, I have a 2 that can come out. And then I have to put the 1 over x together with the x to the 1/2. Any questions? What does that integrand turn out to be? When I simplify that algebraically, what is 1 over x times x to the 1/2?
X to the negative 1/2.
X to the negative 1/2 again. You're just subtracting exponents. You're taking a 1/2 and subtracting 1. And that's the same thing we just did a second ago, isn't it? We're integrating x to the negative 1/2 again. So we'll get another 2 to pop out to join the 2 that's already out there. That'll give us a 4. And then it'll be x to the 1/2, which is square root of x. That's the antiderivative. It is what it is. So what's that saying? Such is life, or thus is life. Have y'all heard that saying before? Such is life.
C'est la vie.
Yeah. It was a famous last words of an ex-girlfriend to me. It's the last thing she said to me. I messed up. I was an asshole. All right. We learn, right? Okay. So we're plugging in now E, and then we're going to plug in T. Any questions? I'm going to move this down because I might need a little more room. So I'm going to do limit. T goes to 0. I have 2 things. Plug in, see what we get. Okay, when I plug in E, I get 2 square roots of E times natural log of E minus 4 square roots of E. Okay. And when I plug in T, I get 2 square roots of T natural log t minus 4 square roots of t. I'm going to go ahead and handle the part out here that's kind of easier to deal with, because that's just a number. Do we all know that the natural log of e is 1? Okay, good. So that's just 2 root e minus 4 root e. That gives me negative 2 root e. So the first part looks good. Second part is a limit that I have to do. I'll do this limit as t goes to 0 here. All right, pay attention. Things are about to get a little weird. Okay, this piece here goes to 0. I don't think anyone would disagree with that, right? And we have subtraction in front of it. So that just goes to minus 0, so it's basically going away. This part here is the part that we're going to have an issue with, because the square root of t goes where? As t goes to 0, the square root of t goes to
0.
0. Okay, but we have natural log of t. That part, as t approaches 0 through positive numbers, because we're coming in from the right, we already said that that goes to negative infinity. And we are multiplying these two answers together, right? And 0 times negative infinity is an indeterminate form from Cal 1. We can't say what the answer is, which means we've got to go work that limit out on the side and figure out what it is. We've got to take the limit as t approaches 0 from the right of the square root of t times natural log t. Now, I didn't bring the 2 with me. I left the 2 there because I really don't care about the 2. The 2, I can just multiply it back in when I'm done. So how do we do this? When you have 0 times infinity or 0 times negative infinity, how do you approach this? Because we want to use L'Hopital, but we can't yet. What do we do?
Drop one of them.
Drop one down. Okay, so which one do you want to drop?
Square root of t.
Square root of t. Good. I like to drop anytime I have a power of t, I like to drop that down. So I'm gonna be thinking that t, square root of t is really t to the half, and I'm gonna drop it to the bottom, so it's gonna become t to the negative half. And now that guaranteed is in a form of either 0 over 0 or infinity over infinity. It's guaranteed that that's the case. So I can use L'Hopital at this point. So I apply L'Hopital's rule. This will become the limit as t goes to 0 from the right. The derivative of the top, derivative of natural log t, is 1 over t. And the derivative of the bottom is negative 1/2 t to the negative 3/2. That doesn't look very nice, but it's going to clean up algebraically. I'm going to go ahead and take this negative 1/2 that's on the bottom, and I'm going to flip it up to the top and make it a negative 2. And then I still have a 1 over t there. And then I'm going to bring this t to the negative 3/2 up to the top as a t to the positive 3/2. And that will allow me to combine these two together. So that should just get me limit t approaches 0 from the right of negative 2 times just t to the half, right? That's what we get there, which is the same as square root of t. And now take your limit, and that limit goes to 0. All right, so we can say then that this goes to 0, and then we had the 2 in front, right? So we had the 2 out here, and the 2 can come out here. It doesn't matter. Everything there is gone. So our answer is negative 2 square roots of e. So it converges. Any questions on that? So on a test, all right, if you get to this point right here, and you tell me that that's equal to 0, without showing me any work, I'm going to take points off. Okay, even if you get it right, that it's 0, you have to show me because it could possibly have not been 0. It depends on what this limit does. And sometimes that limit will go to infinity, and sometimes that limit will go to a number that you wouldn't even think it goes to. A good example of that is this limit. This is a classic limit that hopefully you saw in Cal 1. If you had proper instruction, then you should have seen that limit in Cal 1. What happens in this limit is that this piece goes to 0, and then that piece is going to infinity. So what you wind up getting is that in here, everything in here is going headed towards 1, but it's never actually 1 because you're adding something. That 0 is some little tiny piece. So it's headed towards 1, but it's being raised to the infinity. But remember, this 1 is actually just a little bit bigger than 1. So you get this indeterminate form. And if you run through all the stuff you're supposed to do with this, and this would depend on your teacher. For me, I create an equation, I do natural log on both sides, but you'll wind up figuring out that nobody wins, that the answer to that is E. So it's like the 1 doesn't win and the infinity doesn't win. It's like some weird compromise and the answer turns out to be E. So I'm just saying, when you get to a thing like this, if you get the correct answer, you just got lucky. So I have to take some points off for not showing this work. Okay. I feel like I'm ready to move on. Now you can do all that homework out of that section. There's a problem here that I didn't do. I don't know if y'all can see that, but right there. This right here. So you have a problem. You would have to realize that denominator can be factored, right? And if you factor it, you see that there's a problem at 4 and at 0. But because 4 is the only number in our interval, then we only have to deal with the 4, right? So you have to set up a limit and let t go to 4, approach it from the left side, all that. But after you're all done with that, you have to find the antiderivative. And to find the antiderivative, you're going to have to be able to figure out how to do the antiderivative of a constant over a factorable or reducible quadratic. And so that would require some partial fraction decomposition, right? So again, things are coming up from the past. I want to show you something else. This is an exam 2 that you just took from a year ago. And I want you to see now that on this exam, I included, so we covered more during this semester, the traditional semester. On that test, they had to do an improper type 1 integral, right? It's type 1 because obviously negative infinity is there. But look at this one right here. That's a type 2, right? You've got a problem at 1, and 1 is in this interval. And then this one right here is another improper integral because you got infinity there. But look at, to do the integration on this, that's partial fractions, right? So these would be some good problems to look at. Oh, what about this one up here? Is this one right here a type 2? Do we have a problem? Well, you'd have to see if you can factor the denominator, which in this case it does factor. It's x minus 3, x plus 2. And so you have a problem at 3 and at -2, but our interval only goes from 0 to 1. So this is not an improper integral. So you just do that the traditional way. But of course, you still have to do this like long division and then whatever else after that. So I think you might agree with me that this test was a little more involved than the one that you had because you had that added element of the improper integrals could be there. All right, we're ready to move on. You all ready? Chapter 7. Y'all are awfully quiet today. All right, so I'm going to start this out. Fresh page, new chapter, chapter 7, applications of integration. So now that we know, I mean, the good news is this: we can kind of like be like, yay, we're done with the techniques of integration. We have now all the tools that we need to start doing applications of this. All right. So the first thing we're going to look at, 7.1, is areas between curves. Before I start it though, I want us to make sure that we understand the foundation of where the formula that we have for area underneath the curve comes from. And I know we've done this already, but I want to point it out because the geometry of what I'm about to put up here is important. Not necessarily for this section, but for the next section. So the idea came that we started with the function f, right? This was some function of x. We started at a, ended at b, and we tried to find the area underneath this. So what we did was we drew rectangles, right? And we put an infinite number of rectangles in here. But before we went to an infinite number, we just imagined that we had rectangles. Right, so we had all these rectangles in here. I'm just putting a bunch of them in here. And then what we said is, okay, let's try and find a formula for a single rectangle. All right, so we just imagine taking that rectangle over here and saying, all right, do we have a formula to find the area of that? Well, the width of it was the same for each rectangle. And if you go back to when we were doing it, it was like b minus a over n or something like that. But we later on just called that the dx part of the integral. Because remember, we got the fundamental theorem of calculus, which gave us this wonderful result. And I had told you when we were looking at this to look at the dx as being the width of the rectangle and look at the f of x as being the height of the rectangle. And that comes from the idea that if we want this height right here, well, that's going to be the distance from the curve down to the ground. And that's just the function's value at some, given x value. So this was f of x. So if we wanted a formula for the area, I should have put here, area of a single rectangle, then the area of the single rectangle would be f of x times d of x. That's the width times the height, or height times the width. So once we found a formula for the area of a single rectangle, we said, let's add them all up, right? Let's add them all up. So we use the integral to add them all up. What are we adding up? We're adding up these areas. And we're going to move the rectangles, starting them over here on the very edge at A. And we're going to just imagine moving the rectangles across, right? Having an infinite number going from A to B. And that's where the A to B comes from. All right. So everything within this right here corresponds to something geometric that we can look at, right? Something that we can associate that formula with in a picture. So now what we want to do is add this other element to this where we have two functions. We have a function f, and now we have another function which I'll call g. And what we'd like to do is, again, start at some value a and end at some value b. And we'd like to figure out what the area between these two functions would be. Okay, so can we come up with this area? Now, for this picture that I'm drawing here to make sense, we need to agree on something. F is bigger than G on this interval. So where we're looking, in the yellow region, do you all agree that the F function is on top of the G function? It's above it, right? So as long as we can all agree on that just to start, then if I wanted to find the area, what I would do is imagine, again, cutting this up into an infinite number of rectangles. All right, bunch of rectangles in here. Now, if I take one of those rectangles over here to the side and I take a look at it, can we come up with a formula for it, for the area? Well, how wide is it? How wide is this rectangle?
The
Well, we're
DX.
going to do the same thing, right? So dx, that'll still be dx. What's different now is how tall the rectangle is. So we need to know this height. And can somebody tell me what it would be?
F of x minus gx.
Yeah, it's the top function, right? So what we have for this rectangle is we have a top function, and then we have a bottom function. Now, in this case, f is the top function and g is the bottom function. So the difference of those two should be that height of that rectangle. So that should be, for us, the f of x take away the g of x. That's our height. So the formula that we have for the area of a single slice or single rectangle should be f of x minus g of x, that's your height, times d of x. So the area of a single little piece, right? And now what do we want to do? If we have a formula for one of them, we want to add up an infinite number of them, right? So we want to do the integral of that formula and we want to vary the value of x between a and b. And that is the formula for finding the area between two curves where the f is always on top of the g. Now you'll hear me say this, instead of using this formula, you'll hear me say top minus bottom, okay? Because for me, I don't care if we call it f or g. I just want to know which function was on top and which one was on bottom. That's the thing that's important to me. Any questions? Okay, let's do an example. In my lecture notes for this section, I have a little bit of a better picture drawn here than I did for you, but it's there, okay? It's there if you want to look. I always like to restart. I hate putting notes up and just pointing to things. I like to just create it as I go. I think it just goes, I think it's better for you when I do it that way. All right, so where's my first example? All right, there we go. Okay, so our first example is this. Let me just copy this and bring it over. I don't want to give away anything. I don't want to show you the picture of it yet. So. All right, so you are going to now have to dust off the part of your brain that has these functions that you learned in algebra and pre-cal and Cal 1. These functions that are common functions that you should know how to draw without having to go to your graphing calculator. Like everyone here should be able to draw lines. Everyone should be able to draw parabolas. You should be able to draw square root functions, you know, sine functions, cosine functions. We kind of have like a toolbox full of functions that we should be comfortable with. The two that I've presented here, I would say everyone here should be able to draw without needing a calculator. So let's look at them. We're gonna sketch the region bounded by these two curves, and then we're gonna find the area of that region. All right, so let's do it. So I'm gonna start off with just a general picture here. Y equals 2 minus x squared. Let's start with that one. That's a parabola, right? Because it's x squared. It opens down because there's a negative in front of the x squared. And the 2 means that I move it up 2. So I go up 2. I'm going to say that that's 2 right there. And this parabola opens down like this. Oh, wow. It's not the best parabola in the world, but good enough. There we go. All right, so that's the blue one. And then I have the red one here. That's just a line. Y equals negative x is just like y equals x, which is the identity, that diagonal line, but it's got a slope of -1. So it just goes like this. All right, those are the basic sketches of those two lines. We are supposed to now find the area of the region that is bounded by those two. So you need to realize that we are talking about this region here. What is that area, right? Now, I think it would be worth it for me to label these things. This blue one, I'm going to call it f of x because it's on top, is going to be 2 minus x squared. And then the red one, I'm going to call that one g of x because it's on the bottom, is the negative x. Also, do you all understand that that we're not talking about this green area over here, or we're not talking about this area? Do y'all understand why it's not those green areas? Because it's not bounded, right? Like those areas continue forever. The only region that's bounded completely by both of those curves is the part in yellow. All right. So there's only one place we could be talking about. So now what I do is I imagine, again, I have a rectangle in here. Now, you might be ready to go right to the formula right now, okay? And that's great, but I'm trying to look ahead for what we're gonna do later on in this chapter. I think it's always useful to understand what's going on here. We have our rectangle. We know that its width is dx. And we know the height of it. Let's see, the top of this thing is always the blue function. And the bottom of this thing is the red one, right? So this distance from here to here should be the 2 minus x squared, that's the top one, minus the bottom one, be careful, minus, right? That's your top minus bottom. And so I can go now and start to set up the integral. I have the integral, it'll be the 2 minus x squared minus the bottom function, negative x, all of that dx. Any questions? Integral top minus bottom. We're all right? What am I missing? What do I still need?
Interval.
The interval.
Yeah, the limits of integration, like the actual interval. So where am I going to start my rectangles and where am I going to end them?
The first point of intersection and the second point of intersection.
Correct. So we imagine that we've got rectangles that go all the way over here. We got rectangles that go all the way over here. So each of those rectangles, they're going to start wherever these two curves intersect, and it's going to end where those two curves intersect. So we've got to figure out those x coordinates. So how do we find the intersection of two curves?
Calculator?
No.
You set them equal to each other?
We set them equal to one another. I mean, yes, we could use a calculator to check our answers, but algebraically, we want to set them equal to one another. And so I set the top, it doesn't matter which one you put on the left or right, you just set them equal to one another. And that's a quadratic equation. Like everyone here should be able to solve a quadratic. I'm gonna move everything to the right side. So I got a positive x squared minus x and then minus 2. And luckily for us, because this is the first example, that factors.
Wouldn't that be plus X?
I moved everything to the right
Oh,
instead of the left. If you move it to the left, then it would be plus, but then you would have to probably get a negative out of there anyway. So no matter which side you move it to, you're going to get the same two answers. 2 and -1. Those are the x coordinates of the point of intersection. So I'm going to put those here, -1 to 2. Yes? Okay, now we have to do that integral. Now on a scale of 1 to 10, where 10 is the hardest integral that you've done, and 1 is the easiest integral you've done, where do you rate this?
2.
2?
2.
2, yeah. Yeah, because this is just 2 minus x squared plus x, right? dx. Just distribute, like get rid of the parentheses. That's just all like basic stuff, right? So from here on out, you will not see me finish these problems, all right? Dot, 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 you can do that. You're gonna get a numerical answer. That numerical answer will represent the area. On your next test, I'll probably have you maybe do one problem, maybe 2 problems where you have to calculate the entire answer. Like you got to go all the way down to the number. The rest of the test, you will be boxing that as your answer. It's going to be all about, can you translate the problem into the math problem? And once you get it to the math problem, well then, yeah, we can do that, all right? So the challenge is taking it in whatever form it's given to you, whether it be like this area between these two curves, or it be some other abstract idea that we're going to get into. Once you get it to the integral, we're happy, all right? Next one. Yeah, I like this one. Okay, so same thing. I want us to find the area of the region bounded by these curves. Okay, so find area, sketch. Okay, I want you to sketch, and then find area of region bounded by these curves, whatever. Sometimes we call lines curves, all right? Even though they're not curved, we still refer to them as curves sometimes. All right. Do y'all see that we have 3 curves? We have 3 things here? Okay. So first one, square root of x. That's what square root of x looks like. Now look, when I do my sketch, I might wind up realizing after I put them all here that I need to start over and do them again because my graph was too small, or I need more of my y-axis or something. The first sketch is always just to make sure you understand what they look like. The next one, that's a line, has a slope of 1. It's been moved down 2. That's a terrible slope, but it'll work. I should label it. Well, I'm not going to label them yet. You can tell with the colors what they are right now. Let me do, let's see, green. The last one, what's y equals 0?
Just the x-axis.
The horizontal line.
Oh,
Horizontal,
yeah.
x-axis, it's the x-axis. Horizontal line through y equals 0. Okay. Now, do you see the region bounded by all three? It's right in here. Right? That's the region bounded by all three. So, We're going to be putting rectangles in here, right? So we got rectangles, you know, they're all over the place in here. All these rectangles. Is there a way that you can find me a formula for a single rectangle? Like if I pick this rectangle here, can you tell me, well, first, can you tell me how wide it is?
D of x.
Dx, it'll always be dx, okay? All right, now, can you tell me the height? So which is the curve that's on top of this one? Isn't it, it's the blue one, isn't it?
Be blue over red.
And then the bottom is the red one?
Yep.
Okay, and that means that this distance should be the top one minus the bottom. The top one is, I'm going to label them over here. This was square root of x, right? That's that function. The red one was x minus 2. And then, of course, the green one was y equals 0. So the blue one minus the red one would be the square root of x minus the red one. Okay, so is that our formula? Are we ready to do this? Or does someone see we have a problem?
What about the rectangles that are bounded by just y equals 0 and then the square root of x?
Yeah, so
Yeah.
this formula that we came up with applies to some of the rectangles, but not all of them. The ones over here on the left-hand side, actually, there's an important point right here, right there, where everything to the left of that, the blue's on top and the green's on the bottom. But if you go to the right of it, the blue's on top and the red's on the bottom. Do y'all see how there's this like natural split in this thing we're trying to find the area of? So how do you think we should address this?
We're going to need two equations.
Yeah, we're going to need to split it into two separate integrals. One of them will deal with the left side, where the top and bottom functions are always the same two functions. And then we'll do the other integral, which will do the right side, which will do the other two functions. But if we're going to split the integral, we need to know where to split it. And we also need to know where it starts and where it stops, like the whole thing. So it might be worth our time right now to try and figure out, where does this start? Where does this happen? And where does that happen? So how can I find the first of these question marks?
It's at the origin.
It's 0, right? We don't need to do any work for that. I mean, as long as you know what you're graphing, like we know that that's 0. Okay, so we know that that's 0 just by inspection, by looking. Do we know this second question mark?
Two.
It's 2, and that's because that's where this red one hits the x-axis, right? So that's where this red one is equal to 0, which happens at 2. Okay, so that one we did also by kind of inspection. What about the last question mark? Isn't that where the red and the blue meet? So it's the intersection of these two. So why don't we set them equal to one another then? Okay, so I need to find the intersection. I'm running out of room, so I'll do it over here. The intersection of the red and the blue is going to be setting the red equal to the blue. Now that is not a quadratic equation. That is what's referred to in college algebra as a square root equation. And can anyone remember how you solve that?
Square both sides.
Square both sides. Okay. Now, when you square both sides, whenever you square both sides of an equation, you should have this big light bulb go off in your head that says, I better check my answers. Okay. Anytime you square an equation, you introduce the possibility of what are called extraneous solutions, answers that don't actually work. So we'll have to check our answers. No big deal. We'll do it at the end. All right. So we square both sides. We actually have to expand the left-hand side. That means like FOIL it out. And then we'll move X to the left, subtracting it on both sides. And again, this one factors. -4, -1. We get two potential solutions, 4 and 1. And I think it's obvious that it has to be 4 because this is 2. Obviously, it has to be to the right of that. But you could check real quickly that if you plug, let's see, if you plug 4 in here, you get 4 minus 2, which is 2, and then the square root of 4, which is also 2, so that works. But if you plug in 1, it doesn't work, because 1 take away 2 is -1, and the square root of 1 is +1. So you get -1 equals +1. So that second answer is an extraneous solution. But we got what we needed. We needed to know that that was 4. All right, zoom this back out a little bit. So what we're going to do now is we're going to set up our two integrals. The first integral is going to go from 0 to 2. And when we're doing that integral, the function that's on top is the square root of x. And we're subtracting from it the function that's on the bottom. So what's the function on the bottom in this first little region here?
Y equals 0.
Y equals 0. Now I don't need to write 0, but I'm going to just to stress again, that's top minus bottom. Then we'll add to that whatever we get when we do the integral from 2 to 4. And this time we can use that formula that we came up with earlier. It's the blue one on top minus the red one dx. And now each of those could be done. ... Okay. Let me see what the next example I have looks like. Yeah. Let me at least, I think we have enough time. How about this? Y equals sine x, y equals x equals pi over 2, x equals pi. We get to draw now. We have to draw a sine function. We know that sine is bounded between 1 and -1. We know that pi has, that sine has a period of 2 pi. So it does an entire cycle in that space. So halfway is pi. Pi over 2 is here. 3 pi over 2 is here. So I'm going to draw myself a little sine function. Here it comes. Here's my blue sine function. Starts out at 0. At pi over 2, it's at 1. At pi, it's at 0. At 3 pi over 2, it's at -1, and then back to 0. So it looks something like this. Okay, there's my sine function. Now it goes the other direction too, right? It goes this way. I don't need to do it, but just remember it does go that way. Then we have the line y equals x, which is the identity. So you have to be careful here because I know it cuts through. I'm not quite sure where it cuts through, but it does cut through. And then we want green function, which is, what is x equals pi over 2? What is that if I draw it?
A
It's a
vertical
straight line up and down.
The vertical line, so it looks like this. And then I'm running out of colors, we'll do it in orange. X equals pi, which looks like that. Okay. We have a little bit of a problem. And the problem is that my picture isn't good enough for me to figure out what the region is we're talking about. And the reason it's not good enough is because I don't know for sure where this red line hits the blue. I don't know. So the accuracy of my graph here is having an impact on my ability to do this problem. Do you all see that? I feel pretty good about the sine function, but let me rethink the red one for a second. Where is 1 on this graph? Where's 1 on the x-axis? So I guess what I'm saying is, what's pi divided by 2? It's a little bit bigger than 1, isn't it? Right, it's a little bit bigger than 1. So that means 1 is over here, isn't it? 1 is to the left of that. And so the identity function, y equals x, if I go to the right one, I should go up 1. I should be like here. Do y'all see that this point should actually be on my red line? And so when I draw this, it should actually do this. Like that. See, I drew it incorrectly in the beginning because I didn't know if I needed to be that accurate. Do y'all see the region bounded by all of them? It's that region right there. If you were to draw rectangles throughout this region, are you always having the same top and same bottom the whole time? Is it always the same top function, same bottom function? Yes?
Yep.
Okay, the top function is what? The red, right, which is x. The bottom function is what? The blue, right? So that's the sine. The only thing left is the limits of integration, but that's given to us, right? That's the left and right boundaries of that region, which are the pi over 2 and the pi. So that integral, right, this definite integral, that used to just be a problem I would give you and you would get an answer and you wouldn't have any idea of like what that meant or like the meaning of that. Now it represents this very strange area, right? So you can work the rest of that out. All right, so for homework, what you need to do is finish up 6.6. You don't need to necessarily start 7.1. Just make sure you understand 6.6. We've got to come back. There's more to do in 7.1. Then we get into 7.2 and 7.3. Those are where we start doing volumes, 3-dimensional stuff, which is going to be fun. All right, any questions? All right, that's it for today then. Everyone have a great weekend already. Yeah, it's Wednesday, right? Yeah, so have a good weekend. If I don't see you in my office hours between now and then, I'll see you next week. Okay, thank
See you
you.
later, sir.
Have a good weekend.
Too.